Once we begin talking about intervals of increase and decrease, we come up with a very direct method or a way of focusing our attention into finding what are referred to as extrema. Extrema is just a general term to say we're trying to find any maximum values or minimum values that our function takes on. So when we say extrema, that means find any minimum or maximum function values. But using that word extrema gives us a more condensed way to say that. Looking at our first graph in example 13, this is one that we were working with in a previous example. We know that it's increasing to the right of the y-axis, decreasing to the left of the y-axis. Whenever a function changes between increasing and decreasing in either order, the point that we end up with there is either a maximum or a minimum. In this case, it's a minimum because the point 0, 0 is a lower function value than any of the points around it. If we follow the curve a little bit to the right or a little bit to the left, our function values are increasing relative to this point 0, 0. So, so we have a minimum, and we can actually be a little bit more precise with this. We can refer to this particular minimum as an absolute minimum. It's an absolute minimum because at this point, the function takes on its smallest function value. There is nowhere where our function value dips below y equals 0, giving us an absolute minimum. If our function changes from increasing to decreasing, that's an obvious place to look for a minimum or a maximum. Another is if our function has an endpoint. In this case, we have an increasing function. It's never changing to decreasing. In one direction, the function is continuing on and on, but at the left end here, we have a terminal point at 0, 0. In this case, since the graph doesn't continue on to the left, there are no function values that dip below 0. We again have an absolute minimum at the point 0, 0. An absolute maximum would look like one of those graphs just flipped. So if we had a curve like this, our function is increasing, changes to decreasing. That point at the top would be an absolute maximum. Since it's the maximum value in that area, but also the maximum function value that the curve ever takes on. In example 14, we want to do the same. We want to find all extrema. In this case, we have 2 because we can see that our function is changing between increasing and decreasing. That's kind of again, a key thing, a key behavior to pay attention to. And what we have is a point at -6, 7 and a point at 2, -1 where that behavior is changing between increasing and decreasing. -6, 7 is a point where our function is taking on a larger function value than any others around it. So we would refer to this as a maximum, but it's not the largest point overall because our function keeps increasing over on the right-hand side. Since it's not an absolute maximum, we'll refer to it as a local maximum. The function does take on larger values in other locations, but in this small region, that's the highest point that we hit. Similarly, for 2, -1, our function does continue down on the left-hand side, so this is not an absolute minimum, but it is a local minimum. So we want to make sure we know how to identify a maximum or a minimum function point, and then indicate whether that's a local or an absolute max or min. And again, the difference is really just looking at the endpoints of the graph, the behavior. In this case, in example 14, our function is continuing to decrease, so it's continuing to head down, and it's continuing to head up, versus what we had in example 13. We had a function that was only increasing on both ends. So that 0.00 was the absolute lowest function value that curve would ever hit.